Jona Vetterli, and I'm gonna try to pronounce the name of your company. I hope I get it right. Luege and Meyer. Okay, I'm terribly sorry about that. Jona received his structural engineering degree in 2020 from Lucerne University of Applied Sciences with a focus in building envelopes. And your case study today, the greenhouse, the pavilion glazing through the interplay of structure and facade. The greenhouse is the center of a new public park, Operaparken in Copenhagen, in a harbour, which was developing in a competition in 2019 and finalized in 2023, right? And you're going to talk us through that great-looking pavilion. Okay? Thank you.
I'm very happy to be here and to take you to the process of the development, the planning, the challenges, and fortunately the realization of this very interesting glass pavilion. First, I'll give you some background information about the project, and after that we will look into some aspects of the development phase and then dive into the details. Finally, I can show you some pictures of the execution. The Operaparken project is located in Copenhagen harbour on the island right next to the Danish Opera House. It's a public park that is currently being completed. The park was designed by Cobe Architects in a competition in 2019. Among other things, the park area the park has a parking space for over 300 cars, a pedestrian bridge to the Opera House, and a lot of greenery will be created. In the model picture on the right, you can see the pavilion in the center of this green lung, which contains a coffee shop and the exit from the parking. We were very happy to join this interesting project at the end of 2020. First as facade engineers from Zurich, and shortly after also with our structural engineers from Lausanne, which were responsible for the steel construction. Our partner in Denmark helped us on site with the meetings, the plannings and the execution. The project was already on an advanced stage of planning at the time, and we joined, and we were able to start on very good foundations. The client is AP Moller Foundation. They were also very high involved in the planning process. As already mentioned, Cobe were the architects of the project. The engineers from the concrete structure were Vita engineer from Denmark, and the steelwork were executed by HSM Industry. They were included in the project on a very early stage, which in my opinion was very important for the succession of the project. At this point, I would like to thank our project partners for the very good and interdisciplinarity, the creative ideas and the openness for new ideas. This is the vertical section of the pavilion. In the center is an atrium that extends over 3 stories and has a lot of greenery in it. In green is a curved glazed atrium facade, and here on the ground floor in red is this ground floor facade, which is also curved. In orange, you see cores and the columns, which are the support for the steel roof in green. In blue. The pavilion measures approximately 40 to 40 meters and has the form of a flower. On the left side, you can see the complex steel structure of the roof, and in green, this ground floor facade. In my presentation, I will only focus on this ground floor facade and the steelwork. Then we have 3 cores in concrete and 3 columns that are the supports for the steel roof. The previous structural design is shown here. The steel roof is supported on the concrete structure and also on the glass facade to lower the deflection of the steel roof. But in a case of fire, the steel structure must also hold without this glass facade. These were the glazing units that were used as columns for the steel roof. The build-up was 3 × 8 mm with a stiff interlayer. And the force that came from the roof were up to 170 kilonewtons, which is approximately 17 tons, so it's very much. Through our experience from the Operaparken Museum, we knew how much finesse, glass testing and execution control would be required to design this glass. If you compare the project with related buildings where such glass facade, load-bearing glass facade were used, the difference is very clear. Compared to the Steve Jobs Theater on top and the Operaparken Museum in the middle, we have some columns and concrete cores in the pavilion. Our structural engineer from Lausanne then came with a brilliant idea. He had the idea of constructing the roof using the principle of pre-stressing. This way we could reduce the deflection without putting any stress on the glass facade. The principle can be explained using this model. In the first step, the steel construction is pre-shaped upwards. Then this pre-shaped steel construction is pulled down using tension rods. And if you now apply a force, it just reduces this pre-stress in the rods and with basically 0 deflection compared to the previous model on the left, where we have the force directly on the glass facade and very high deformation. The principle also works with our complex structure. The pre-shape is up to 112 millimeters, depending on the stiffness of the roof, because it's a varying geometry. Then the roof is pulled down to the desired height to reach the final geometry. After that, we could apply the tension rods, which I will name tension lamellas in the facade area, and then release the pull-down device so the load transfers to the tension lamellas in the facade. After that, the canopy is applied, and also we could mount the glass facade. The pre-stress in the lamella is designed to be about 10 kilonewtons per lamella when everything is finished. But in the construction process, these pre-stress were much higher. You can see this here. On the left, we have right after the releasing of the pull-down device, the maximum tension is on 50 kilonewtons. Then in the permanent load case, we're about 10 kilonewtons, and with upward winds, it rises until 90 kilonewtons in these tension lamellas. Of course, this change means an additional element in the facade. However, by comparing the glass joints with other projects that appear very transparent, it quickly becomes clear that the joint is very small. This way we were able to convince the client and the architects that also with the tension lamellas in the facade, it's still a very transparent building. The red section is our glass joint of the Operaparken project, and the Operaparken Museum, for sure it was isolated glass, but you see this in the middle picture, it looks very transparent, even with much bigger glass joints, and this is because of the size of the glasses, basically. A variety of materials and positions for these tension lamellas were tested. In the end, we used a duplex stainless steel, which was mirror polished. It measures 25 to 6 millimeters. The position on the right was the solution we took that is made now, where the lamella is visible from the inside. Now for the facade, the structural systems changed a lot. For example, if we have horizontal deflection of the steel roof, which is one unit, each glass is affected differently. So we had to make sure that the glass can tilt in every direction freely without applying stress to the glass. This is the statical system we used. The glass is pin supported in the center and on top, and on the edges we have some radial supports which blocks the rotation of the glass unit and takes the wind load. On the right side is the statical the calculation model for the glass unit. So we have linear support on bottom and top, which is done with metal profiles and free glass edges over the whole height. It was very interesting to see how the radius affects the stiffness of the glass. So to make, for example, the 6-meter radius is less stiff here in the edges, and if you lose the curvature, you lose some more of the stiffness of the glass, and thus the stress is higher and also the deflection. With the simplification of the facade, the glass structure could of course be reduced. The glass build-up. We were able to change from 3 times 8 millimeters to only 2 times 8 millimeters with an interlayer from Tosifold centric glass extra. Also, the LT value from the glass, the transparency is much higher. We have less weight and also a reduction in global warming potential, it's basically CO2. The weight is 40 kilograms for the second. Here you can see the glazing profiles. These are made of stainless steel and are bonded onto the glass. The eccentricity from the supports had to be taken into account in every single calculation. This is the view from the outside. We used the same brackets we used for the tension lamellas, also for the glass mounting. And to take some tolerances in the position of the bracket, which has very high loads from the tension lamellas, these brackets were welded directly on site to some inlaid or cast-in steel plates. The other tolerances we could all take with screws, so we can change the height of the bracket, for example. Here's a bit more detailed. This is the bracket that was used for the lamella and also for the glazing profiles. And the center brackets, which is the pin support for the glass units, were only for the glass facade. And here in green you can see the lamella, which is a bit to the inside of the glass unit. In the vertical section it looks like this. Those are the glass units and then the tension lamella on the inside. The bonding onto the lamella were planned but not executed due to some high tolerances. The structural bonding to the glass shoe had to be pretty stiff. We were working very closely together with Dow, and we used the Dow Seal 993 for this bonding to the glass shoe. But in the other case, when the glass units were tilted, they have to go with the tension lamella, which is this line here, and this gives a shearing force to the bonding. So we wanted to have less stiffness, low stiffness here, and use silicon Dow Seal 121. The steel structure was produced in 3 parts at the HSM industry. On the right bottom here, you can see the pre-shaping with a thermal impact. This is the roof, how it's built together on site with these 3 parts, and the cantilever were mounted afterwards. We had, unfortunately, some very high tolerances of about 40 millimeters. This is why the pull-down process was a very iterative work to find the final form and geometry of the roof. But after a few attempts, the roof was on the right height. Those are the tension lamellas, and on the right you can see a glass unit which is mounted. Also here, unfortunately, in these glazing profiles, we had a lot of tolerances, and to take those, the bonding onto the glass shoes were executed on site to have more options to take the tolerances. This is also the mounting of the facade, and here you see the top brackets. Again, this bracket takes the tension lamella and the glass unit, and the center bracket just for the glass. This is the lower bracket, the pin support on the left side, and the tension lamella with the wind support for the glass unit on here. And here in this hole, it can move freely in all directions, basically. Just for the wind, it's blocked. The left, you see the column and the complex steel structure. And here again, tension lamella and the glass unit. This is the lamella from the inside, and here you see it's not really working together sometimes. Sometimes it's very good, and this is why the bonding onto the lamella were left out. But the mirror polish, this looks really nice. This is the side view from this spring, with now the greenery on the roof was applied. And I'm looking forward to see the final project. With approximately the same steel weight, we were able to save 9 tons of glass, and which means about 16 tons of CO2 equivalent, just through this design change. The timeline was very short, and this leads to quick decisions, which were supported by the whole team. We worked with direct supplier for the glass and also the glass glazing profiles, which leads to the problem for the responsibility of the tolerances. And I think in the next time I would design with more tolerances if we work like this. The last challenge was a bit the language and the distance, but I learned that engineering is an international language and you can talk with everyone, even if the language doesn't apply. Thank you very much.